When we turn our instruments toward the heavens, we expect the universe to tell us a coherent story. For decades, our standard model of cosmology seemed almost untouchable. It laid out a clean, elegant narrative of how the cosmos expanded from a hot, dense point into the vast web of galaxies we see today. But sometimes, a single landmark observation can shatter our most comfortable assumptions. When the James Webb Space Telescope opened its golden eye to the cosmos, it was meant to confirm what we already suspected. It was built to peer back to the very dawn of time and capture the faint infant light of the earliest structures forming in the darkness. But what I saw in those early images, and what astronomers around the world are now struggling to explain, was not a simple confirmation. It was a profound mismatch deep in the primordial universe at a time when only small, fragile seeds of galaxies should have existed. James Webb found fully grown cosmic giants, massive, brightly shining galaxies that simply should not have had enough time to form. It is as if you walked into a nursery and found fully developed adults sitting in the cradles. This is not just a minor accounting error in our astronomical charts. This is a fundamental challenge to the very timeline of cosmic evolution. Either our understanding of how gravity pulls matter together across billions of years is deeply incomplete, or something even stranger was happening in the early moments of creation. If you are drawn to these deep, haunting questions about the true nature of reality, take a moment to subscribe to Brian Greene Theory. Together, we are going to explore what happens when the universe breaks our rules. Because what James Webb may have uncovered is not just an anomaly in the night sky. It might be the first crack in our understanding of physics itself. To understand why astronomers are in a state of quiet panic, you first need to understand how we thought the universe was built. For the longest time, we had a beautiful, perfectly functioning blueprint. We call it the standard model of cosmology. It is a story of slow, meticulous, almost agonizingly patient construction. Think about how a great metropolis comes into existence. You do not wake up one morning to find massive steel skyscrapers, sprawling subway networks, and millions of people living in perfect orchestration on an empty plot of land. You start with a small settlement, a few humble structures. Over generations, people gather, roads are laid, small towns merge into larger cities, and step by step, the complexity grows. The architecture of reality was supposed to follow the exact same logic. We call this bottom-up structure formation. In the beginning, after the explosive birth of our cosmos, the universe was little more than a vast, expanding ocean of hot, glowing gas. It was mostly hydrogen, a little helium, and absolute darkness. But hidden within that darkness was a secret architect, dark matter. Now, we cannot see dark matter directly, but we know it is there because we can feel its gravitational pull. Over hundreds of millions of years, dark matter slowly clumped together, creating immense invisible webs and gravitational valleys across the cosmos. Imagine a vast, rolling landscape covered in deep craters. If it rains, the water naturally flows down into those craters, pooling at the bottom. In the early universe, dark matter created the craters, and ordinary gas was the rain. As this hydrogen gas fell inward, it compressed, heated up, and eventually ignited into the very first stars. But these were not galaxies, not yet. They were just tiny, chaotic clusters of starlight, the cosmic equivalent of a few campfires in the wilderness. According to our ironclad laws of physics, gravity takes time to do its heavy lifting. To build a mature, majestic spiral galaxy like our Milky Way, you need billions of years. You need those small, primitive clusters of stars to smash together, merge, settle down, and pull in even more gas. It is a violent, messy process that demands an enormous amount of time. You simply cannot rush gravity. This was not just a guess on our part. This narrative was baked into our most sophisticated supercomputer simulations. We could plug in the laws of physics, let the simulation run for 13,800 million years, and the digital universe would grow up to look exactly like the real universe we see around us today. We were so confident, we thought we had cracked the code of cosmic evolution. But physics is an observational science. To truly prove our blueprint, we had to go look. Because light takes time to travel through space, moving at a strict speed limit of 300,000 kilometers per second, a telescope is literally a time machine. This is not a metaphor. When you look at the moon, you are seeing it as it was a little over 1 second ago. When you look at the sun, you see it as it was 8 minutes ago. So the strategy was simple. Hurry. If we build a telescope powerful enough to see light that has been traveling for 13.5 billion years, we will see the universe in its absolute infancy. That was the primary mission of the James Webb Space Telescope. We parked it 1.5 million kilometers from Earth, shielded it from the heat of the sun, and opened its enormous beryllium mirrors to the deepest, darkest patches of space. We were ready to look back at the cosmic dawn. We were ready to see the primitive, scattered campfires of the first stars. We fully expected to find small, ragged, unformed proto-galaxies struggling to pull themselves together in the dark. We expected to find the wooden huts of the early universe. But James Webb did not show us wooden huts. It showed us massive, sprawling cosmic cities. And it showed us these giant galaxies existing at a time when the universe itself was barely out of its infancy. The foundation we had built our entire understanding of the cosmos upon was suddenly shaking beneath our feet. When I tell you that we built a telescope to look back in time, I want you to understand exactly how that works, because the physics is beautiful. The universe is expanding. Space itself is stretching. Imagine drawing a wave of light on a rubber band. If you pull the ends of the rubber band, the wave gets stretched out. The crests and troughs move further apart. This is exactly what happens to light as it travels across the expanding cosmos. The longer light travels, the more the expansion of space stretches its wavelength. By the time the brilliant, high-energy ultraviolet light from the very first stars reaches us, after traveling for over 13 billion years, it has been stretched so far that it is no longer visible to the human eye. It has shifted completely out of the visible spectrum and into the infrared. We call this cosmological redshift. This is why the Hubble Space Telescope, as magnificent as it is, it could only see a wall of darkness when it looked at the absolute cosmic dawn. It was looking for visible light that was no longer there to seize the beginning of everything. We had to build an instrument that could feel the heat of that stretched, ancient light. That is why James Webb is an infrared telescope with 18 massive hexagonal mirrors coated in a microscopic layer of pure gold. It was designed to capture a ghost. And what a ghost it found. When the data from the deep field observations came back, my colleagues and I sat staring at our screens in disbelief. We were looking at a period roughly 500 to 700 million years after the Big Bang. In cosmic terms, this is a blink of an eye. This is the universe in its absolute infancy. We expected to see tiny, chaotic smudges of light, baby galaxies. Instead, we found monsters. Astronomers quickly dubbed them universe breakers. We saw galaxies that were so incredibly massive and dense that they seemed to hold as much stellar mass as our own Milky Way. But our Milky Way had billions of years to slowly pull its spiral arms together. These newly discovered giants achieved the same massive scale in a fraction of the time. But the mystery goes much deeper than just their size. It is their maturity that defies logic. In the standard model of cosmology, early galaxies are supposed to be messy, irregular, and primitive. Yet, James Webb revealed galaxies with distinct structures. We saw disks and spheroids, complex shapes that we thought required billions of years of gravitational settling to form. It is like discovering a beautifully crafted Swiss watch buried in the mud of the Jurassic period. It is entirely out of place in time, and the chemistry is wrong. The very first stars were made of nothing but hydrogen and helium, the pristine gas forged in the Big Bang. Elements like oxygen, carbon, and nitrogen, the heavier elements that make up rocky planets and eventually us, are only created inside the intensely hot cores of stars. They are released into the cosmos when those stars explode in violent supernovas at the end of their lives. So the early universe should be clean, lacking these heavy elements. But when we analyze the light from these impossible galaxies, we found them glowing with the signatures of heavy elements. Oxygen was already there, swirling in the cosmic gas. This means that entire generations of stars had already lived, burned out, and exploded. How? When? There simply should not have been enough time on the cosmic clock for all of this to happen. Then comes the most terrifying puzzle of all, the black holes. At the center of almost every large galaxy today, including our own, sits a supermassive black hole. They are the gravitational anchors of the cosmos. For decades, we believed that galaxies formed first, and then slowly black holes formed in their centers, growing over billions of years by swallowing surrounding gas and dust. But Webb has found supermassive black holes sitting in the early universe, fully grown and devouring matter at terrifying rates. They are so massive that they challenge our understanding of how black holes even form. It suggests that in some cases, the black hole might have formed first, acting as a massive gravitational seed that rapidly pulled the galaxy together around it. The pieces of the puzzle are all there on the table, but they no longer fit together into the picture we thought we knew. The universe is telling us a story that we do not yet know how to read. To dive deeper into how these rapidly forming galaxies and massive black holes are forcing physicists to rethink the dawn of the cosmos, this documentary breaks down the timeline inconsistencies perfectly. Listen closely. The reality you experience every day hides a terrifying and fascinating secret. We have always assumed that the laws of physics are universal, constant, and unbroken across time. But the James Webb Space Telescope is forcing us to confront a paradox so deep, it threatens to unravel everything we thought we knew about the dawn of time. To understand this paradox, we have to talk about gravity. Gravity is the ultimate architect of the universe, but it is incredibly weak. Think about it. You can pick up an apple from a table. In doing so, your arm is successfully defeating the gravitational pull of the entire planet Earth. Because gravity is so weak, it requires immense amounts of time to accomplish anything on a cosmic scale. Pulling scattered clouds of primordial hydrogen gas into dense pockets, igniting those pockets into stars, and gathering billions of those stars into a cohesive, rotating galaxy is a process that demands billions of years. It is a slow, methodical accumulation. But then we look through the James Webb Space Telescope and we find galaxies existing barely 300 million years after the Big Bang. In the grand timeline of a 14 billion-year-old universe, 300 million years is absolutely nothing. It is the morning of the very first day. Yet, these newly discovered galaxies are breathtakingly bright. They are massive. They are swirling with heavy elements like oxygen and carbon, which tells us that entire generations of stars have already lived and died within them. This is the paradox. Imagine you are a detective. You walk into a room where a candle has just been lit. You know the exact moment the match was struck. But when you look at the candle, it is already melted halfway down to its base. The wax has pooled and hardened on the table. The physical evidence completely contradicts the timeline. How can something be older than the time it has been allowed to exist? We are caught in a logical trap, and there are only two ways out. Both of them force us to rewrite the textbooks. The first possibility is that our understanding of astrophysics, how stars are born, how they live, and how they die, is fundamentally flawed when it comes to the early universe. Maybe the cosmic dawn was not a quiet, slow gathering of gas. Maybe it was a violently chaotic epoch. Some of my colleagues propose that early galaxies experience explosive, frantic bursts of star formation. Imagine immense clouds of gas collapsing all at once, igniting millions of supermassive stars simultaneously. These monstrous stars would burn with blinding intensity and then explode as supernovas in a cosmic blink of an eye, churning out heavy elements and blowing gas back out into space, only for it to collapse and ignite again. This bursty star formation could make a baby galaxy look incredibly bright and deceptively mature, mimicking the slow growth of a massive galaxy like our Milky Way. In this scenario, the universe was simply much more efficient and violent at building stars than we ever gave it credit for. But there is a second possibility, and it is far more unsettling. What if the astrophysics is correct, but our fundamental cosmological model is wrong? For decades, we have relied on a framework called the lambda-cold dark matter model. It is the bedrock of modern cosmology. It tells us that invisible dark matter provides the gravitational scaffolding for galaxies to grow. But what if dark matter behaves differently than we thought? What if, in the extreme conditions of the early universe, dark matter clumped together much faster, creating supercharged gravitational wells that pulled in matter at impossible speeds? Or worse, what if the nature of gravity itself was subtly different in the infancy of the cosmos? If the scaffolding of the universe formed faster than our equations allow, then we are not just tweaking a detail about star formation. We are tearing out the foundation of modern physics. We are admitting that the universe is governed by hidden mechanics we have yet to discover. This is why physicists are losing sleep. James Webb did not just take pretty pictures. It handed us a contradiction. We are staring at mature cosmic cities standing in the realm of the infant universe, and we are forced to ask a chilling question. Is our cosmic clock wrong, or is the universe hiding a profound secret about how matter and gravity interact? The deeper we look, the more the paradox tightens its grip. To really grasp how deeply this breaks our understanding of reality, we have to go beyond simple astrophysics and look at a radical, brain-breaking possibility. What if we have the entire sequence of cause and effect completely backward? For over half a century, the story of cosmic creation seemed straightforward. First came the Big Bang, then came the gas. The gas cooled and slowly clumped together under gravity to form the first stars. Those stars burned through their nuclear fuel, died, and collapsed to form the very first black holes. Over billions of years, these black holes grew, merging with one another, while stars gathered around them to form galaxies. In this classic picture, black holes are the children of stars. They are the ultimate endpoint of stellar life. But the images from the James Webb Space Telescope are whispering a radical alternative into our ears. What if black holes were not the children of stars? What if black holes were the parents? Imagine walking into a pristine forest and realizing that the colossal mountain at its center was not formed by slow tectonic shifts over millions of years, but was dropped there overnight, fully formed, and then the forest grew around it. If supermassive black holes existed in the infancy of the cosmos, weighing millions or even billions of times the mass of our sun, there is simply no way they could have grown that quickly by slowly consuming dying stars. The physics of feeding a black hole puts a strict speed limit on its growth. When gas falls toward a black hole, it heats up through friction and glows with intense radiation. That outward pressure of light acts like a wind, pushing away incoming matter and preventing the black hole from devouring gas too quickly. To reach the immense sizes James Webb is seeing so early in time, these black holes would have had to violate that speed limit continuously since the moment of creation. Which brings us to the truly mind-breaking idea, primordial black holes. What if these cosmic monsters did not form from collapsing stars at all? What if they were forged directly in the violently dense, turbulent foam of the Big Bang itself, fractions of a second after creation? In those extreme initial moments, quantum fluctuations could have been compressed so intensely that space and time collapsed directly into massive black holes without ever needing a single star to exist first. Think about what this means. If primordial black holes were scattered across the infant universe before the first atom of hydrogen even cooled, they would have acted as the ultimate gravitational anchors. They would not be waiting for gas to slowly gather over hundreds of millions of years. Instead, these pre-existing behemoths would pull in surrounding gas with ferocious speed, compressing it rapidly, igniting stars, and assembling massive galaxies almost instantaneously. In this inverted reality, black holes are not the dark graveyards of dead stars. They are the seeds of creation. They are the catalysts that jump-started the universe when it should have been a cold, dormant void. And it gets even stranger. If primordial black holes or direct collapse mechanisms were active, it means the very texture of the early universe was fundamentally different from what our standard models predict. It suggests that quantum mechanics and general relativity were locked in a violent, macroscopic dance during the first seconds of time, creating structures that we are only now beginning to detect 13.8 billion years later. We are forced to confront a profound shift in perspective. We thought we were looking at a quiet, orderly universe that took its time growing up. Instead, we may be living in a universe that hit the ground running, seeded from its very first second with black holes that dictated where galaxies would be born. It flips our entire understanding of cosmic evolution on its head. Here is the hard truth that every theoretical physicist, including myself, has to confront when the data refuses to align with our equations. Nature is under no obligation to conform to our aesthetic preferences or our mathematical comfort zones. For decades, we felt a deep sense of pride in the standard model of cosmology. We believed we had built a cathedral of understanding, a framework so robust that only minor details remained to be filled in. But the James Webb Space Telescope has laid bare a reality we can no longer ignore. Our cathedral may have been built on sand. The hard truth is that our standard model of the universe may not just need a light tune-up or a minor numerical correction. It may be fundamentally incomplete, or in the worst-case scenario, plain wrong. When we look at the history of science, this is not an isolated incident. It is a recurring pattern. At the end of the 19th century, physicists believed they were approaching the end of physics. Isaac Newton's laws of motion and gravity had explained the cosmos for centuries. James Clerk Maxwell had unified electricity and magnetism into a single breathtaking set of equations. The universe seemed like a clockwork machine, fully understood, and then a few small, very annoying anomalies appeared. The orbit of Mercury refused to obey Newton. The speed of light refused to change, no matter how fast an observer moved. Many scientists dismissed those anomalies as tiny measurement errors or minor puzzles that would soon be solved within the existing framework. But those tiny puzzles were not minor glitches. They were the first tremors of a catastrophic seismic shift. To solve them, Albert Einstein had to burn down the Newtonian worldview. He had to show us that space and time are not absolute, very rigid backdrops, but a dynamic, flexible fabric bent and warped by matter and energy. We are sitting at that exact same historical crossroad today. The impossible galaxies and oversized black holes discovered by James Webb are our modern Mercury orbit anomaly. They are telling us, in no uncertain terms, that the equations we have trusted for 40 years are failing when applied to the dawn of time. So what does this hard truth force us to consider? It forces us to re-examine dark matter. For half a century, we have postulated that 85% of the matter in the cosmos is invisible, cold dark matter that interacts only through gravity. It served as the silent scaffolding for galaxy formation. But if dark matter cannot pull gas together fast enough to build these early massive galaxies, then our definition of dark matter is wrong. Perhaps dark matter is not cold and passive, but warm, interactive, or dynamic. Or perhaps dark matter is a phantom, a placeholder for a breakdown in our understanding of gravity itself. It forces us to re-examine dark energy and the expansion rate of the universe. If the universe was expanding at a different rate in its earliest moments than our current models predict, our calculation of cosmic time could be off. When we say a galaxy existed 500 million years after the Big Bang, we are calculating that age based on our model of expansion. If that model is flawed, then the cosmic clock we use to measure the age of the universe is ticking at the wrong speed. Admitting this is uncomfortable. It forces us to swallow our intellectual pride. We spent decades telling the world that we knew the story of creation from the first fraction of a second to the distant future. Now, we must have the courage to look at the night sky and say 3 words that are the true lifeblood of science. I do not know. We do not know why the early universe was so hyper-efficient at building stars. We do not know how black holes grew so large so fast. And we do not know if our current laws of physics can bridge the gap. But this hard truth is not a defeat. It is a thrilling, extraordinary invitation. It means there is still something profound left for us to discover. For me, as a physicist, this is the most deeply exhilarating time to be alive in nearly a century. I remember the exact moment the first deep field images from the James Webb Space Telescope were downloaded and processed. My colleagues and I were gathered around glowing screens, expecting to see a quiet, dimly lit cosmic dawn populated by small, fragile fragments of newborn stars. We expected a confirmation of our life's work. Instead, the screen lit up with impossible jewels. We saw monstrous, blazing galaxies existing barely 300 million years after the Big Bang. We saw evidence of colossal galaxy collisions churning out heavy elements at a time when the universe was supposed to be a pristine, undisturbed ocean of hydrogen. In that single moment, a profound sense of vertigo washed over us. A lifetime of comfortable cosmological assumptions simply evaporated. The universe, as it turns out, has a wonderfully ruthless way of shattering our pride. Instead of tying a neat little bow on our standard model of cosmology, this telescope has thrown us into a beautiful, terrifying crisis. The cosmos is standing there, looking back at our sophisticated supercomputers and our elegant mathematical models. And it is firmly telling us that we missed something fundamental. But I want you to understand something crucial. This is exactly what science is supposed to do. A crisis in physics is never a failure. It is the birth pangs of a new understanding. Every time our equations break down, every time we find an anomaly we cannot explain, an impossible galaxy or a black hole that grew far too fast, we are not losing ground. We are actually peeling back a layer of the cosmic illusion. We are getting closer to the true bedrock of reality. We are being forced to let go of our comfortable illusions and reach out into the dark for a deeper, more profound truth about gravity, dark matter, and the very fabric of space and time. We are actively tearing down the old cathedral of physics to build something far more magnificent. We are living through a scientific revolution. The textbooks are not just being updated with minor footnotes. They are being rewritten from scratch right now, in real time. And the most beautiful part of this revolution is that it does not just belong to the astronomers and the theoretical physicists hidden away in university laboratories. It belongs to all of us. It belongs to you. The questions we are asking at the edge of the cosmos: where did everything come from? How did the universe actually begin? And what are the hidden rules that govern reality? These are the most fundamentally human questions we can ever ask. They are your questions just as much as they are mine. That is exactly why I pour my energy into Brian Greene theory. I want to bring you to the absolute frontier of human knowledge. I want to take you to the edge of the unknown so we can stare into the abyss together and try to make sense of the shadows. But exploring these deep mysteries, translating the complex mathematics into clear, undeniable logic, and bringing these cinematic cosmic journeys to life takes an immense amount of time, relentless research,